I am so psyched for this video, but then again, when am I not psyched for a video? This one is all about the general concept of why tangent line approximations work and how they're related to distance equals rate times time. Now, I'm going to warn you, this also goes over differentials too. Some of you will never have to study any of this at all. But those of you in AB or BC Calc, I find this video to be a really neat segue between what you're learning right now with derivatives and what's coming up in the not too distant future. Ooh, very cool stuff. So let's check this out. So what's the deal with the general concept? Well, essentially what we've been doing, as we've seen before, is you've got a point, we'll call this curve f of x right here. And you've got the point c comma f of c, that's some point on the curve. And we saw that we found the tangent line at c f of c. And what that does is we find a value on that tangent line and it approximates a true value on the curve. Okay, so let's take a look at this overall. Our tangent line approximation would be y minus f of c is equal to the slope at c, which would be f prime of c times x minus c. That's your tangent line approximation. Now, I want you to look at this a little bit closer. This is pretty rad, depending on how you want to look at it. One way of looking at this is y minus f of c. Well, what is this y value right here? Well, that's this. That's the y value on the tangent line, right? So you've got some new x value in the tangent line, and this y value is right here, the y value at that point. So overall, if we take a look at it, y minus f of c is this distance right there. We call that, do you know what we call that? We call it dy, right? So that right there, this entire length here is dy. This amount right here can be called delta x, but it's often written as being equal to dx. A very small change in x would be dx, and dy is a very small change in y. So dy is equal to the derivative, f prime of c, right, at that point, times, this is essentially dx, x minus c. It's a change in x. Ooh. Now in general, if we have just any old x value here, we would have dy equals f prime of x dx. Nice! So what's this all about? Well, to get a little bit closer, the true change in y would be the true y value on the curve minus the y value that we have on the curve at the beginning. So this right here, this part right here is delta y. So dy is this. We use it to approximate delta y, which therefore is approximately f prime of x dx. Okay, why does this make so much sense? Think about it. The change in y is like your displacement or a change in position. Oh, you see where this is going? F prime of x is your rate. It's your velocity. Oh, dx is this change in time. This is all just distance, or displacement I should say, equals the rate times the time. Oh, that is just gnarly and cool. Okay, let's take it a little bit further. One other idea is that the y value, if we're approximating it, so the true value on f of x is where this y value is. If we add f of c to the other side, f of x, this value right here, is approximately f of c, we're adding that to the other side, your starting value, plus f prime of c times x minus c. So we've seen that before. Well, let's go a little bit closer. This is essentially your starting value, right? Call it y initial plus f prime of c is the derivative, right? So that could be just f prime of x times dx. So another way of looking at that is we start out at some y value, we add on to that how fast we're going times how far we've traveled. So your start plus how far you've traveled gives you your f of x, which is your finish. And if some of this isn't clicking yet, that's okay. But it will be clicking in the not too distant future, I promise. And you know, if it doesn't from this slide, that's okay. The big realization though is that point slope form has always been the displacement equals the rate times the time. Oh, all right. So what are differentials? We actually already saw them. Right? So a differential is that dy right here. And we saw that dy is equal to, right here, f prime of x, the slope, times the amount that we've changed in the x direction. That's it. We've already seen how it's a part of point slope form now. So dy is a differential, dx is a differential. They're small changes of x and y based from this tangent line, and they approximate the true change in y, and delta x becomes dx as delta x gets very small. Very cool. So if you have a teacher that ends up asking you for the differential dy for each of the following, it's very simple to find. There's two ways of thinking about this. You're essentially taking the derivative with respect to x on both sides. So we would get the derivative of y with respect to x is just dy dx, and the derivative of x cubed is 3x squared. Then we're going to multiply both sides by dx. So essentially you're saying the change in y divided by the change in x equals the slope. So the change in y would be equal to the slope times the change in x. Or displacement equals rate times time. Whoa, goosebumps, right? I got some. That's cool. Now the other way of looking at this is you can just right away get right to this and be like, okay, well, dy equals the derivative, 3x squared dx. Other people look at that as dy is equal to f prime of x dx. They're all different ways of looking at the differential. Okay, so let's look at this one. So again, dy, right, that'd be the change in f of x, is equal to f prime of x dx. And just fill it in. So we have the differential y, small change in y is approximated by, or equal to, the derivative. Well, what's the derivative of that? Well, that's going to be, remember this is x squared minus 5 all raised to the 1/2. Little chain rule action, so we're going to get 1/2 times x squared minus 5 to the negative 1/2 times 2x, little chain rule, dx. All right, there's the differential in x. Now remember, all this is saying is take the derivative, multiply it by dx, and that gives you dy. The 2's cancel out. We get x over negative exponent, the square root, that's from the 1/2, x squared minus 5 dx. That's it. So again, remember, a small change in y is equivalent to the rate at which we're changing, the slope, times a small change in x. Distance equals rate times time. Oh, beautiful. Now, there's one other thing we can do with this. Many calculus classes skip over like everything I'm going over in this video. I still think it's worthwhile. This last problem, I'm just going to barely mention a little bit about something called propagated error and what that is. And I'll do like an exercise on it. Some calc classes have this in it. Many don't. I know A, B, and BC do not, but some teachers like going over it. It's not so bad. When you're doing any kind of measurement in the real world, what we essentially use the mathematics for is we say, let's let delta x, the change in x, be the error in the measurement. And let's let x be the measurement. So what does that mean? So let's just pretend that you measured something to be, I don't know, 11 inches, right? We measured something to be 11 inches. That's your x value. And we say that the error is, I don't know, maybe plus or minus 1 inch. It's a pretty bad error, plus or minus 0.5 inches. That's delta x. That's the possible change in x. So if we know the exact error, let's say that we know the exact error is plus 0.5 inches, then the exact value would be 11 plus 0.5 inches, making it x plus delta x is the true amount, right? And we'll never know the true amount when we measure. So when we measure, there's error. The error is delta x. We add that on to the measurement to get the true amount. Okay, so what is propagated error? Okay, well, propagated error would be if you have an entire function that we're using to calculate, I don't know, something like I did the area of a circle. So you take the true value, so this is the true measurement, the true amount, plug it into the function that gives you area or volume or whatever it is, and you subtract from that the, well, this would be the estimated amount. And if you take the true value minus the estimated value, you're going to get a change in those values. That's delta y. Or you'll get what's called the propagated error, right? The error in your measurement. That's it. So delta y is the error. Delta x, right? So delta y would be the error in the overall formula. Delta x is the error in the part you measured. Let me show you something that makes this a little bit more simple now with area of a circle. And we'll practice using calculus to figure it out. And that'll be it. So let's say you have a circle here and you measure it, right, to have a radius of 3 centimeters, but your error is plus or minus 0.1 centimeters. So that's delta r. we want to know what is the propagated error, which means how much is the error off by. We want to know delta A, right? What's the amount we're off by the true value? That's the true value minus the estimate gives you the amount that you're off by, right? So the area is pi r squared of any circle. It's not r. A of r is therefore pi r squared. And so delta A, we know, is approximately dA, right? It's approximately a small change in A. Okay, where do we go from here? Well, we know that dA is equal to the derivative of A, so that'd be A prime of r, times dr. Just like it was dy equals f prime of x dx that we saw in that last little part of the video. Okay, so what's dA? That's going to be your propagated error. That's the amount we're off by, the change in the error between the true value and the estimated value, the value we got when we measured. So we take the derivative. We do what this says, which is going to be pi times 2r times dr. And what this will represent is, again, the amount that we're off by, a rough estimate of the error. So this would be pi times 2 times, the radius we measured was 3. However, the amount we were off by was plus or minus 0.1. Okay, so multiply all that through. You've got 2 times 3 is 6, times 0.1 is 0.6. So that's going to be 0.6 pi, and that'll be plus or minus 0.6 pi. That equals dA. And remember, what that represents is a change in the area between the true value and the estimate. So this would be the approximate error we'd be off by, given how much our measurement error is and how much our original measurement was. It's not the easiest concept to necessarily understand at first, but just think of it step by step as I went through it, and I hope it made some sense. Propagated error is not too bad. So if you have to go through it, you will rock it. You know what we're going to be rocking? Some exercises in the next video, though. Peace.